Let us look at the equations in the steady state, that is assuming that the motor is running at a constant speed, the load torque is constant, the power supply voltage is also constant. As a result, the derivative terms become 0, there is no change of speed, so d omega dt is 0, there is no change of armature current, so di dt, dia dt is equal to 0, and because of that the equations become simply algebraic equations, and therefore they will be the applied voltage EA will be equal to the back EMF will be kb times omega m, the motor speed, plus only the armature drop term RAIA, the LDID term is 0. And the second equation is the mechanical system torque equation. The torque is KT times the armature current, and that equals the constant load torque TL plus the frictional torque KF into omega m. The moment of inertia term J d omega dt is equal to 0. So these are the steady state equations. What information can we get from here, or how these equations can be made use of for the purpose of designing our control system for the motor? Now this is where I will take some very simple numbers so that we don't get bogged down in detailed calculations and numbers with 3 or 4 places of decimals and what not. But in practice the numbers will not be such nice rounded off numbers, and one will have to work with the calculator and sometimes even the computer to make detailed calculations. So keep this in mind that I am only using some very simple round figures so that we can understand the point without getting lost into all the computations. Now what was the objective of our control system or the drive? The objective is to drive the load at a particular speed. So the load, there are two aspects of it which are there in this equation about the torque, namely the load torque and the desired speed omega m. As we have seen, the product of these two, the load torque into the desired speed or the speed at which the load will run, gives you the power, the mechanical power that is to be spent on the load, and that much power, and in fact a little more, has to be provided to the motor. That is the electric power that will be taken from the supply. So the mechanical power Pm is equal to the load torque TL into omega m. Now depending on the particular load application of these three numbers Pm, TL and omega, two of them will be specified. In the grinding wheel example, perhaps based on some previous experience or measurement, one will be able to figure out what is the load torque when you are doing a particular grinding operation, what is the resistance of the surface being ground, and therefore what is the torque that is required, and of course the speed at which the grinding wheel should operate. A practical grinding wheel will have to operate perhaps at a much higher speed than whatever numbers we will select. Similarly, the torque number that we will choose will also be just for our convenience of calculation and does not reflect any actual figure. So let us choose some rounded numbers. Omega m, for omega m we will choose a speed roughly corresponding to 1500 revolutions per minute, 1500 rpm, and there is a reason for this particular figure 1500 rpm. The 1500 rpm figure arises in the following way. Remember that the power supply that we normally get in our house or in an industrial establishment is an alternating current power supply, and in India our frequency is 50 hertz or 50 cycles per second. You can think of that roughly as 50 revolutions per second. of some generator somewhere, and therefore that will correspond to 3000 revolutions per minute. And as you know, it turns out that depending on the number of poles on the generator that you have, or the number of pole pairs, because the poles come in north south pairs, the generator will have to be run at an appropriate speed. This is what actually happens in a generating station, and therefore there is a speed control problem at the generating station itself. The generator, of course, is not driven by a motor. The generator is driven by a turbine, a hydraulic turbine in the case of hydroelectric station, or a steam turbine in the case of a thermoelectric generating station, or a thermal generating station. In order to produce an AC voltage of 50 hertz frequency, therefore it will be necessary to maintain the turbine speed at a constant value, and turbine speed control, and in addition to the frequency, of course, the generator voltage has to be maintained constant. So the voltage control, these are two major control problems in a generating station: voltage control and frequency control, frequency of the AC produced, but that is dependent on the turbine speed. So essentially it amounts to controlling the speed of the turbine, maintaining it reasonably constant, and maintaining the generator output voltage reasonably constant. So there are two major control problems in a electric generating station. Anyway, for the moment, the figure therefore 3000 rpm can be understood as 50 hertz or 50 cycles, and if you think of a cycle as a revolution, then 50 cycles or revolutions per second amounts to 3000 revolutions per minute. And since you have at least one pole pair, therefore the frequency at which the generator should run will be 1500 rpm. It can run, of course, at a lower speed. If you have more poles, then more pole pairs, you can run the turbine at a lower speed. Typically a steam turbine can be run at a high speed, whereas a hydraulic turbine will run at a lower speed. Therefore a steam turbine driving a generator, or an alternator as it is called, will require a smaller number of pole pairs for the alternator, and for the hydraulic turbine it will be a larger number of pole pairs. So that is the reason for choosing this number 1500 rpm. An actual grinding wheel may run much faster than that, and in fact I will make some further rounding off as we go along. Otherwise, as I said, I will have to write down several places of decimals. Now 1500 rpm, roughly how much is it as in terms of radians per second? Now these are some of the calculations which as engineers one should be able to do mentally without putting down or using the calculator. Rough calculations I am saying, not precise figures. So once again 1500 rpm, just as 3000 rpm corresponded to 50 hertz, 1500 rpm will correspond to 25 hertz. 25 hertz. So 25 into 60 is 1500, that is how 25 hertz. Remember the expression for the sinusoidal voltage that I wrote down earlier, it had something like A for amplitude into sine into omega t, where this omega is called the frequency, angular frequency for the power supply voltage, and it of course as you can see corresponds to some turbine rotating somewhere. So this omega, although it is the frequency almost, not quite f, but omega is 2 pi f, where f is the frequency in hertz. This omega will be what? 1500 rpm corresponds to 25 revolutions per second. So with that omega will be 2 pi times that, and therefore omega will be nearly 50 pi. Omega, the angular speed in radians per second, is 50 pi. A better way of thinking about it, since this 2 pi f business is more electrical than mechanical, will be one revolution is 360 degrees, and how many radians is that? Now everybody knows that it is 2 pi radians. So in fact we talk about 360 degrees as an angle of 2 pi radians, right? So one revolution is 2 pi radians, so 25 revolutions will be 2 pi into 50, 50 pi radians in a second. So omega will be roughly 50 pi, and maybe as we proceed we will take it approximately as 150 radians per second, just a rough figure. Precisely, of course, it will be 50 pi, and you can take pi to whatever number of decimal places, it will be a little more than 150 radians per second. So that is omega, the motor speed. Now the torque, we have to take it in Newton meters, then the product of the two, the torque in Newton meters and the angular speed in radians per second, will give us the mechanical power in watts. Now as I said, one may be used to thinking of power in horsepower units, though nowadays because we are using the international system of units, one would use the watt or the kilowatt as the unit of power. So thinking of that, then Pm, the mechanical power, is load torque into omega m. Omega m is about 150 rad per second. So if I think of a motor power of the order of let us say we are thinking of a motor which is about 5 kilowatt, or the load which requires a power of about 5 kilowatt. So what will be the magnitude of the torque? It will be 5 kilowatts, so that is 5000 watts divided by 150, that is a little more than 30, so let us say 30 Newton meters. As you can see, what I am trying to do is I am trying to cook up an example so that we can work up with some simple figures and get some idea of what is really important and what is it that needs to be done. So now I can pose the problem like this: a load requiring 30 Newton meters maximum torque is to be driven at a speed of 1500 rpm. That is where the problem will start. Here is a particular mechanical load which requires at a speed of 1500 rpm a torque of so many Newton meters. What kind of motor should I buy? So you can see how the calculations go. Omega m is known, TL if it is known, one calculates the mechanical power. In this case 30 Newton meters into 150 rad per second will be about 4500 watts, and so one will say, well, I will choose a motor whose capacity is more than that but not much more than that. So maybe a 5 kilowatt motor or a 6 kilowatt motor, depending on what is available off the shelf, one will go for. Okay, so the load torque that is to be provided at a specified speed are now known to us. So we have two figures and we have the mechanical power. Now of course the motor is being chosen so that it can deliver that much power or even more, so we will have no problem in finding such a motor. What next can we calculate? So if you look at the equations, then you have the motor torque generated by the motor equal to the load torque, which we have found out or which we have assumed is 30 Newton meters, plus the coefficient of friction into the angular speed at which the motor is going to run. So the motor is going to produce more than what the load itself is going to absorb, because some power will be lost in friction. It will appear as heat elsewhere in the bearings, maybe the fan will be turning and so on. So the motor power therefore has to be more than the mechanical power which is to be delivered to the load. And knowing Kf, now how do you know Kf? Well, once you know the load, if you have decided about what kind of motor you are going to use, maybe the motor comes with a fan, you will have to decide what kind of bearings you are going to provide, and then one can sort of set up the drive in a preliminary manner, and if necessary even measure this friction coefficient Kf. So the design is not simply a matter of sitting at the table and just doing some calculations. It will involve going back and forth, looking at the load, finding out what is the requirement, then looking into what is commercially available, cheap, easily, reliably, what kind of motor, quality. Of course we have decided that we will use a separately excited DC motor, so one is only looking for a DC motor. What power? So rough calculations are shown. If you know Kf, of course Kf you will not know completely unless you have chosen the motor to start with, so a little back and forth will enable you to decide as to what should be the motor. So probably if 4500, the product 30 Newton meters into 150 rad per second was about 4500 watts. So with 6 kilowatt as the maximum power output of the motor, probably we are on the safe side. So having chosen such a motor, then one will find out what is this Kf, and those therefore complete the calculation. So what is the result of all this calculation? TL is known, the load torque. Kf is now known, the coefficient of friction of the whole drive. The angular speed is known, so we know the torque that the motor has to produce. The motor will produce torque KTIA equal to this sum. Knowing this then, and knowing the motor torque constant, I have chosen the motor already, so I will know the motor torque constant. I can calculate the armature current IA. So that is the next thing that we will then be able to find out, armature current IA. What next? The motor has been chosen, so we know the armature resistance RA, and therefore we know the armature drop RA into IA, when the armature will carry this current to produce the required torque. Now this plus the back EMF. What about the back EMF KB? We know, we already decided what motor to use, so we know KB. In fact, approximately it is going to be equal to KT. So KB into omega m will give us the back EMF, and so all of this will add up to give us the applied voltage EA. Okay. Now suppose I do all this calculation and I find out that this EA turns out to be, say, something like 256 volts. Now obviously I am not going to be able to find a ready-made DC power supply of this value 256 volts. In the old days, when even houses used to have DC power supply like the AC power supply voltage today, there was a standard DC power supply voltage, and once again it was 230. Although you know that 230 volts RMS is not the same thing as 230 DC as far as electric shock is concerned. So now suppose the power supply voltage available to me, unless I want to design it specially, is 230 volts, but my calculations have thrown up a figure of 256 volts. So what do? Do I go back to choose another motor and things like that? No, because there was one assumption that I was making, so that is something that will have to be decided. The assumption that I was making is that I know KT or I know KB for the motor, but if you remember, I mentioned earlier that these constants, the EMF, back EMF constant and the torque constant, both of them depend on the field current IF. So in fact these two constants are determined by the field current. So when I say I know KT and KB, what I really can find out is, for this field current, what should be KT and KB. So now we will have to do our calculations in a little different manner. We will say that okay, the supply voltage is known to us, let us say it is 230 volts. So 230 volts is equal to, now it is a good approximation that the torque constant and the back EMF constant are proportional to the field current. Of course this approximation holds provided the field current is not very large. If you apply a very large field current, then what is known as saturation can take place in the magnetic circuit, and therefore the flux will not be proportional to the field current. But if you do not reach that level, which normally one will not reach, then the torque constant and the EMF constant will be roughly proportional to the field current. So instead of KB into omega, I can write it as, say, another coefficient into field current into omega. So I will write it as, let us say, K small k subscript b into IF into omega m, that is the back EMF term, plus RA into IA, that is the armature drop. Now of this we know KB is the back EMF coefficient now per ampere of field current per RPM of speed. So it is not just volts per RPM, That was the case with capital KB into omega m, RPM multiplied by volts. Now it will be, or radians per second, now it will be volts per RPM per ampere of field current. So that's this term. The second term is the torque, and therefore there also you will have a KT, small k, torque Newton meters per ampere of armature current per ampere of field current. So I will have KT into IF into IA equal to the total torque which is used up by the load and the friction. So TL plus KF into omega m. Now in these two equations, of course I have assumed already that I use a power supply voltage of 230. So what else is or what is known and what is not known? Omega m is the speed which we want. So we know 1500 RPM or roughly whatever number of radians per second. Load torque is known, armature resistance is known, coefficient of friction is known, and this constant or these two constants, little kb and small kt, in fact they will be nearly equal, which are the torque and the back EMF constant, giving back EMF or torque per ampere of field current and per RPM or per ampere of armature current. These are known. So then from these two equations, what are the unknowns here? The unknowns are essentially the field current and the armature current. Omega m is known, everything else is known. I have assumed that EA I am choosing because of their supply availability as 230 volts. So everything else is known except the two unknowns IF and IA. Now these two equations are fairly simple, although you can see that in one equation I have what is called a linear combination of IA and IF, 230 equal to some number into IA plus some other number into IF, whereas the other equation is some number into the product of IF and IA equal to some other known number. So this is an example of what is called a nonlinear equation, but the nonlinearity is really very simple, just a product of these two currents, and so certainly it is not beyond your capability to solve these two equations for the two unknowns here, field current and armature current. So that at the end of all of this, then you would have arrived at the value of the field current that should be maintained and the value of the armature current that should also be maintained, so that given the constant load torque, specified constant load torque, given the applied voltage 230 volts, assuming that the parameter values are known to 100% accuracy, armature resistance, etc., etc., the motor will run at the desired speed. So this is the DC or steady state calculation which one can go through, which is necessary to proceed further. Of course we can stop here, we can say alright, let us buy the motor, let us get this power supply voltage 230 volts, arrange for the field winding, maybe a resistance in series with the field winding, whatever arrangement, so that the calculated field current will result. You can measure it actually and then set it once and for all, and now you are ready to turn the motor on with the motor shaft, the load mounted on the motor shaft, and hopefully things will go all right. Because there is a problem here which is a practical problem, and as an engineer you cannot overlook it, it is also very important, but it is a different problem of control, namely starting of the motor. A DC separately excited motor is normally not directly started by applying the full voltage, or rather applying the voltage and doing nothing else, and we should be able to see the reason for this. And in fact I mentioned earlier that when the motor starts from rest, the back EMF is 0, and so the electrical equation tells us that the applied voltage EA is equal to RA into IA, that is all. So if EA is 230 volts, the armature resistance, let us say, is of the order of an ohm or less or a little more, the armature current will be of the order of 100 amperes. Now is the motor expected the motor winding, armature winding, expected to carry this kind of a current, 100 amperes? Certainly not for a long time. How do we know that? Well, what was the motor power? The motor power was, let's say, about 6 kilowatts maximum. So that's 6000 watts. That's the maximum motor power. Multiplied, that is equal to the motor applied voltage 230 into the armature current IA. So 6000 watts equal to 230 volts into how many amps? That will give an answer of maybe about 20 amperes. So what we expect is perhaps, and this is what the previous calculation would have shown us approximately, that the previous calculation would have shown us a much smaller current, but in the steady state an armature current of about 20 amperes will be flowing in the motor. Whereas if we don't take any precautions and just connect the motor armature directly to the supply or close the switch, 230 volts, 1 ohm of resistance would result in a current of 230 amperes, 10 times the current which the armature is expected to carry in the steady state. Of course, the motor will pick up speed, but then that depends on the moment of inertia, and we are not looking right now at how the motor starts, how the speed builds up, how the speed changes, etc., because we are only looking at the steady state when everything is constant. So in any case, then one does not start the motor that way. What is done is, in series with the armature, a starting resistance is put, which of course will have to be chosen sufficiently high so that the armature current, when the motor is just starting, will not be such a high value. For example, if the steady armature current value is 20 amperes, then you can figure out how much resistance we should connect. 230 volts divided by 20 amperes will be about, say, 10 or 15 ohms or whatever it is, and therefore we will need a starting resistance of that value. This may have to be a rheostat, because it has to carry a lot of current. It will have to be made of thick wire and whatnot. And in the laboratory, perhaps you have already done an experiment on a DC shunt or a separately excited motor, and you have already come across this problem associated with starting of the motor. So this is a different problem altogether, and it is important. As an engineer, we have to face it and we should know what is to be done. But in the steady state, when the motor has reached the desired speed, when the load torque is there, then the armature current we have calculated, the field current we have calculated, certainly the motor, if it is to deliver mechanical power of the order of 6 kilowatt, drawing from the power supply voltage of 230 volts, the current would be of the order of, say, 20 or 25 or whatever it is, and therefore the motor designer would have taken care of this. When I go to the market and say, well, I want to buy a 230 volts DC 6 kilowatt motor, certainly the motor designer has thought about the armature current that the motor armature will have to carry. So there is no difficulty on that account. Okay, so we are ready with the drive, except for the starting, where one will have to take some precautions, and maintaining the field current constant. Somehow that will have to be arranged. We are through. So why not say that the calculations are over and now we can operate the drive, or if you are going to sell it to somebody, you can say that, all right, I have done the design, take this package. Now of course it is not as simple as that. And what is the reason, or what are the reasons? One thing which we will look into a little later is not the steady state but transient. That is, the motor will run at the desired speed, etc. For example, the starting current must be low. Of course, the series resistance has ensured that the starting current was sufficiently low, but one would like to know what will be the behavior during what is called the transient period, or what will be the transient behavior, something that does not stay on for a long time but is there anyway. When you make a transition from zero condition, motor at rest, to motor running at the desired speed. Another important consideration will be, well, with the load on, how long does the motor take to reach the final speed? Because one would like the motor to speed up to the final speed as early as possible. In fact, again in practice the situation will not be that simple. The motor will be started without any load, that is, the load will be decoupled. As you know, in an automobile or in a scooter, there is this arrangement of decoupling the engine from the wheels, because there is a clutch. Of course, in those cars or scooters where there is a gearbox and therefore there is also a clutch. So this arrangement is usually there. The mechanical load is not just left connected on the shaft all the time, but there is an arrangement for detaching it whenever required. So what one will do is one will start the motor with no load, as it is called. That is, this load torque is absent. Of course, the friction will still be there perhaps. The inertia may be a little lower now because the load is disconnected. And then the motor is brought up to a certain speed, and when it is close to the desired speed, or after waiting for some time, the load is thrown, as it is called. That is, the load is connected. So how long will it take for the motor to build up its speed, so that then I can connect the load and my grinding will start? Remember, the grinding job usually will not start with the grinding wheel at rest. I will have to put the grinding wheel into motion and then only bring it close to the job and start my grinding operation. So there are these additional considerations which are also important, and therefore one will have to look at these aspects of the drive. How much time will the motor take to come up to the no load speed, because you have to wait till that time before you can connect the load. One would like this time to be as short as possible, of course, but it cannot be done instantaneously because there is a inertia. The motor armature has inertia, so it just does not speed up instantaneously. So transient studies will have to be made. What happens between the starting moment and the moment the final conditions are reached and the load can then be connected and it will run at the desired speed, etc. So this is one set of considerations, and we will look at what is known as transient analysis, or analysis of transient behavior of control systems or of systems which are described by differential equations and so on. And for that we will make use of tools such as the Laplace transformation and others. The second thing about which I mentioned earlier was the possibility that things will not be as simple as they look. The load torque may not remain absolutely constant at the value we chose for our design purpose. The grinding job will vary perhaps, and therefore the load torque will not necessarily be the same all the time. One may still like the speed to remain at a desired value. The grinding operation will have to be still carried out at a sufficiently high speed. The supply voltage for some reason or the other may not remain constant at the value that we chose, 230 volts. The field current may not remain constant for some reason. The field is separately excited, therefore there is a separate voltage source for the field perhaps, and that may not remain constant because of some disturbances. And finally, as always, we have assumed that we know all the parameters KT, KB, RA, etc. completely, confidently, up to 100% accuracy, to the last 10th place of decimals, but that we don't, because we make some measurements and the measurements are always inaccurate to some extent and also imprecise. Measuring instruments that we use can only take us up to millivolts or milliamperes or a fraction of a revolution per minute or what have you. Therefore, we cannot assume that we know these parameter values exactly. So one will have to consider the effect of what happens because of these factors. Now some of these can be seen qualitatively, but then one will have to also make actual computations. So what I will do is I will indicate in a qualitative way what we can expect, and then you should go ahead and work out these things at home, working with more exact figures, that is with actual numbers, and not just making qualitative assessment. So for that, let us write down the two equations once again. The applied voltage EA is equal to KB into omega m plus IA into RA, and the torque equation is KT into IA equal to the load torque TL plus the frictional coefficient Kf into omega m. These are the two basic equations, and what we did was, knowing the parameter values, knowing EA, and of course KB and KT were known as in terms of the small kb and small kt, we calculated the field current and the armature current. So having done all those calculations, now let us look at these equations once again and see what is the effect of these things happening. For example, and now when we make this analysis, we have to start with simpler situations but look at more complex or difficult situations. So perhaps one can start off like this: of all these things, EA, the supply voltage, let us say I am reasonably sure that it is going to remain constant at 230 volts, but I am not so sure about the load torque. We made some design calculations assuming a load torque of say 30 Newton meters, but suppose the load torque is less than that or is more than that. For example, at no load the load torque is very close to 0. There is of course the frictional term still, with Kf may be only from the motor and not from the motor and load combined, but TL is 0, that is the no load condition. Normal load will be 30 Newton meters, but occasionally the piece of material that one is polishing or whatever may be a little harder, and so it may increase the requirement of the torque. So the torque may not be 30 Newton meters, but maybe say 35 Newton meters. How much will it be? We really don't know unless one knows more about the practical drive considerations. So what one does is one makes a provision under the assumption that the load torque may exceed what is called the rated value. Rated in the sense we have made these calculations assuming certain values. It is like price of a commodity, it is supposed to be sold at such and such price. Of course you may buy it for more or less. So the rated load torque was 30 Newton meters. So we will allow for an increase in it of how much? Now this is where you have to choose what figures, and then accordingly you will say, all right, my drive will take care of such and such variation. So one may say rated torque plus maybe 10% in excess, or maybe one wants to be a little more not conservative but a little more pessimistic, so we will provide for 20% excess. In fact, we can then advertise that, well, our drive will provide for up to even 20% excess power. So 30 Newton meters normally, but it could be increased by 10% or by 20%. So suppose that happens. EA in our very simple drive, we are just getting 230 volts DC and we are not doing anything about it. So EA is 230, the parameter values, let us assume, are known exactly. So if you look at these equations, then what is going to be the effect of this change of TL from 30 Newton meters to a higher value? A little thinking, and this is where one should not just go and solve equations blindly or in a hurry, but be willing to argue a little qualitatively as to what is likely to happen. And the torque equation tells you what is likely to happen, and one argues this way, that TL is not going to be 30, but it is going to be say 10% more, so 33. Now, if omega m remains the same, of course it may not, but if it does remain the same, then the motor torque will have increased. The motor torque comes from the armature current, so the armature current will have increased. Now, if you look at the electrical equation, the armature current increases the armature drop. Now, if the armature drop is increased, the supply voltage is the same, then the back EMF will reduce a little bit, but the back EMF is proportional to omega m. So, what does all of this then tell you? This qualitative analysis then tells you that when the load torque is increased, my assumption that the angular speed will remain constant will no longer be justified. Of course, the armature current will not be at the old value. What will happen is the speed will decrease a little bit or decrease, and the armature current will have increased from the rated value. So, the drive will no longer run at 1500 rpm. It was designed to run at 1500 rpm under rated conditions, assuming supply voltage was this, torque was this, etc., etc. When the torque is increased, then the speed will be less than 1500 rpm. The armature current would have also increased a little bit. Now, of course, there are some additional complications here which we will overlook, but it is necessary to be aware of it. Now, it is not as if these two are completely independent of each other. There are many mechanical loads for which the torque and the speed do not just behave in any independent manner, and therefore there is what is called, for many devices, what is called a torque speed relationship or a torque speed characteristic of the mechanical load. I am assuming for these preliminary calculations or simple calculations that the torque and speed are independent of one another. That is, the grinding wheel can require a higher torque even though the speed drops a little. So, what one has to do now is, assuming a 10% increase in the load torque, calculate or recalculate or calculate the new values of the angular speed or speed of rotation and the armature current. Speed of rotation is of course our main concern. Now, if 10% increase in load results in 10% decrease in speed, then maybe the situation is not acceptable. But if it results in only 1% decrease in speed, maybe it is acceptable. But if the user wants the speed to not to change by even that amount, but by maybe as little as 0.1%, then one will have to rethink about the whole thing. Similarly, the armature current may go up by 10%, and we have to make sure that the armature current does not increase too much, because otherwise the armature winding will get overheated. Of course, as is the case with any practical situation, there are protective mechanisms that are to put into the circuit. For example, there could be a fuse which will blow out if the armature current increases too much. That is, if you are trying to get from the motor much higher torque which requires a much higher armature current, the fuse will simply blow and therefore the motor will come to a standstill. Hopefully, of course, such things will not happen too frequently. Now, I said earlier that a DC shunt motor, by its sort of very nature, is something which runs at a nearly constant speed. Although if you do these calculations, and I would like you to do these calculations, now for these calculations you can look at your textbook and take the figures from there, or do it the way I have done it, that is, assume 30 Newton meters at 1500 rpm, the values of Ra, you can take some simple number like even 1 ohm, the frictional torque Kf into omega m, we can assume that it is much less than the load torque is 30 Newton meters. How much friction? Maybe 1 Newton meter, alright, choose Kf into omega m equal to 1 Newton meter, so that gives you the coefficient Kf. So, in this way sort of you can cook up an example where you can figure out the values of these parameters, although in practice when I have chosen the motor I get Ra, I can't choose it. Now why is it that the DC motor will run at a reasonably constant speed? And that is the following. If you look at the electrical equation, the applied voltage EA is a sum of two terms. Now typically the armature drop is a much smaller thing than the back EMF. The 230 volts applied does not get used up in the armature drop. In fact, very little of it will get used up in the armature drop. In our example, let us say an armature current is of the order of 20 amperes, it's a high side perhaps. Armature resistance may be as much as say 1 ohm, that's also a little high. The armature drop is just about 20 volts as compared with 230 volts applied voltage, and therefore the rest of it 210 volts is the back EMF voltage. Now if the armature current increases, say even by a factor of 2, the armature drop will increase from 20 to 40, but the back EMF does not become 1/2. Say it was originally 20 armature drop, 230 was the applied voltage, so the back EMF was 210. If the armature current has doubled, so the armature drop is 40, 230 is still being applied, the back EMF is 190. So from 210 it would have reduced to 190, and that's not a reduction of 50%. So although the armature current has gone up by 100%, the back EMF would not have gone down by 50%. Armature current doubled, back EMF is not becoming half, and therefore the speed will not become half. So there is this kind of a built-in mechanism, so to speak. It's not built-in or it's not really designed, but that's the way the shunt motor equations are. That of course this means that the armature resistance has to be small, so I have to use big wire for the winding. I cannot economize by using very fine wire for the armature winding, because then the armature resistance will be high, and that contributes to wastage of power, because that is just what is called the I square R loss, or the heating. The armature gets heated up because of flow of current in it. So if Ra is large, then I square R is also large, and that's a problem also. So usually the decrease in speed and the increase in armature current when the load torque has increased by 10% will not be by 10%, but will be by much less than that. But by what amount, one will have to actually calculate. But this qualitative analysis tells us that if EA remains constant, the coefficients are known exactly, therefore they don't change, we assume they don't change, field current has not changed. Then if TL increases, then omega m will decrease, it cannot remain absolutely the same, and the armature current will increase, it cannot also remain the same. So with change of load torque, the drive cannot operate at constant speed, and therefore one can in this sense talk about an error. If the drive was expected to run at the constant speed, it will not do so if the load torque changes. If the load torque changes, then there will be an error, and so either we have to live with it or else do some redesigning or modify the design in some way or the other, which is of course what we will look into. So do these calculations yourself. For say 10% increase of load torque, what is the decrease in speed, and typically one thinks in percentages rather than absolute figures. Then you can redo it with 20% increase in load torque, what is the decrease in speed like. So what is the speed regulation of this drive, this very simple crude drive? Most probably this will not be acceptable, but this is a first step towards a better design. At the other extreme, of course, we can go to the case when the load has been removed, so TL is equal to 0. When TL is equal to 0, if the frictional part is very small, the torque requirement is very small, then the armature current required also will be much smaller. So instead of 20 amperes, under no load conditions, you may require an armature current of only 1 ampere, let us say. If that is the case, IA is 1 ampere, RA is 1 ohm, then the armature drop is just 1 volt. So the back EMF will be now 229 volts, whereas under rated conditions the back EMF was 210 volts. Now it is 229, which means what? Which means that the no load speed will be greater than the rated speed of 1500 rpm. How much greater? Again, one can figure that out. And this may be acceptable because there is no load connected. The motor may well run at a slightly higher speed than what is desired. But the moment you connect the load of the specified value, everything else is as assumed, the motor speed will return or will eventually become steady at the value that is required. So no load conditions also have to be looked into. Besides that, changes in the load torque, especially on the higher side, this is again something one has to look into. So far we looked at what happens when one of the things which we assumed in the design, TL, is no longer at that value, no longer 30 Newton meters, but 10% greater maybe, or 20% greater, or no load case, so 0. Now we can look at something else. We can look at the supply voltage, 230 volts. Who knows, the supply voltage may go down. There may be other loads that are connected on the power supply, and therefore the supply voltage may go down. Typically it will go down and not go up. So again, then we will have to make calculations. So suppose instead of 230, the supply voltage goes down by 10%. Then what will happen to the speed, to the armature current, assuming the load torque remains at the same value? Now again, qualitatively one can see what is going to happen. EA is less. If the torque is the same, assuming omega m is the same, the armature current is the same, the armature drop remains the same. So if EA has decreased, this means the back EMF must have decreased. But if the back EMF has decreased, that means the motor speed must have gone down. So our assumption that the motor speed will remain constant when the supply voltage decreases is not justified, but the qualitative analysis indicates that when the supply voltage decreases, the motor speed will decrease. By how much? That's again the critical question. So with 10% reduction in supply voltage, how much will the speed go down? As you can see, looking at the magnitudes, 230 volts, 210 volts back EMF, 20 volts armature drop. If the supply voltage goes down by 10%, the armature term, which is small anyway, the back EMF will go down by nearly 10%, and therefore the speed will go down by nearly 10%, not nearly, I mean not exactly 10%, could be a little less than 10%, but it could go down to that kind of a amount. So this drive has this bad feature that if the supply voltage decreases, the speed of the drive is going to decrease, and this is again a property of the DC, separately excited DC motor, that for torque changes the speed changes are negligible, but for supply voltage changes the speed change can be significant. So if we are operating under a situation where the supply voltage is not guaranteed to remain constant but could go down by as much as 10% or even more, then our drive will be unsatisfactory if 10% of speed change cannot be tolerated, and so we will have to do something about it. Now this analysis is still very simple. In one case I assume that everything else is okay except TL is different. Now I am saying everything else is okay except EA is decreased. Now you can see what is going to happen if these two can be combined. That is, unfortunately for us, as ill luck would have it, the supply voltage has gone down and at the same time the load torque demand has gone up. So TL is greater, EA is less. What is going to happen now? Well, the situation is going to be worse. The motor speed is going to decrease still further than it would have if only one of these things had happened. And so one does try to think of such situations. So we may say, okay, 10% increase in load torque, 10% decrease in power supply voltage, what will be the change in speed? In fact, it will not be really acceptable, because already with 10% decrease in supply voltage, the change in speed may be by as much as 10%. So the design is not really satisfactory. These are the two things that one normally worries about. One is the input voltage, the other is the output requirement, the torque, and I used earlier the term disturbance, although for TL it is not really disturbance, it is the main reason for the drive, but EA, changes in EA can certainly be thought of as disturbance. The power supply voltage was expected to remain constant at 230 volts, but it has not remained so because of some disturbance, some load, whatever. So effect of disturbance is to change the performance of the system. It will no longer operate in a satisfactory manner. The change or the error may not be acceptable. The other things that cause some worry is the assumptions that we have made about the parameter values Ra, Kb, Kf in this case. We have perhaps made the calculations on the assumption that the armature resistance is 1 ohm, but maybe somebody made some mistake and it is really 1.5 ohms, or the armature, for some reason the motor has been running for a long time, the armature is getting heated, maybe outside temperature is also high, we have not provided adequate cooling. As a result, the armature resistance has increased by maybe 10% or 50%. So either the value that we chose was not correct or was not known accurately enough, or has changed now because of operating conditions. What will be the effect? Now, as you can expect, if Ra is greater than what it was calculated or assumed to be, then the back EMF term will decrease a little bit, so the speed will decrease a little bit. But you can see that the effect of armature resistance on the speed, or the change in armature resistance on the change in speed, is going to be much less, because there is 20 volts in comparison with 210 volts. But what about the back EMF and the torque coefficient? Why should it change? It may change because it is dependent on the field current, and the field current, I have assumed somebody has made arrangements for it to remain constant, but suppose that arrangement is not foolproof. Some power supply voltage which is connected, to which the field winding is connected, that voltage has gone down, so the field current has gone down by 10%, which means Kb and Kt will be down by 10%. Then what is going to happen to the speed? Assuming the load torque is constant at the old value and the supply voltage Ea is constant at the old value. So change in parameter value, or alternately uncertainty, Kb was assumed to be this much, but there was a mistake done in the measurement, so it is not really that, but it is something else. What would be the values of speed and armature current that would result in the steady state? Now here again you can see roughly what is going to happen if Kb and Kt are less than what it was assumed to be, because let us say the field current has decreased. The load torque, if it remains the same, then the torque equation, the mechanical equation, tells you TL is the same. For the moment, assuming omega m is the same, Ktia has to remain the same, but Kt has decreased, so Ia will increase, the armature current will increase, so the armature drop will increase, so the back EMF available will decrease. In addition, Kb has decreased, so omega m, what is going to happen? Well, there are these two forces working, so one will have to actually calculate and see what happens to the speed. On the other hand, if the field current is increased, then what will happen? So all these calculations have to be done, and this is the kind of thing that people like Bode and Nyquist in the early days, or Black in the early days in the 1930s and 40s were worried about, and these can be roughly said to be sensitivity studies. And in fact, Bode introduced a particular measure of sensitivity. How sensitive are some of the things, for example, the steady value of the speed to variations in load torque, variations in applied voltage, error made regarding the value of kV or kT, or change in the field current, things of this kind. Sensitivity coefficients of various kinds can be calculated, and I will leave it as an exercise to you to look at these two equations and write them in several ways, so that one way will show you, the equation will show you how omega m depends on the load torque. So omega L equal to some coefficient into load torque plus another term, which will then tell you that if the load torque changes by this much percent, then the speed will change by this much amount, and which may amount to so much percent. Similarly, omega n can be expressed in terms of the supply voltage EA rather than the load torque. So that will tell you the dependence of the speed on the supply voltage, and one can do it for each one of the other things. But what we can see right now is that the drive is not necessarily going to be adequate for many practical purposes. So we will have to look into how to get over this problem.